Interstellar travel is not hard, it may be impossible. That sentence sounds wrong, because for decades we have been told the opposite. Rockets are getting stronger, computers are getting smarter, private companies are landing boosters upright on floating platforms. Movies like Interstellar show astronauts bending space, diving into black holes, and crossing galaxies as if the universe is just another ocean waiting to be explored. The music swells, the engines roar, the stars stretch into bright lines, and for a moment it feels real, it feels close, it feels like the next step for humanity. But outside the theater, outside the screen, outside the dreams, physics stands silent and unmovable. The real universe does not care about ambition, it does not reward courage, it follows rules, cold rules, precise rules, and those rules may block us in ways most people never think about. Not because we lack money, not because we lack intelligence, but because the structure of reality itself may forbid the journey. The distances between stars are not large, they are absurd. The speed of light is not fast, it is a wall. The energy required to approach that wall does not grow steadily, it explodes toward infinity. Even stranger, the faster you travel, the more time itself begins to twist. Clocks slow down, mass increases, radiation turns deadly. Tiny grains of dust become bullets with the force of bombs. These are not engineering problems waiting for better technology. These are consequences of the deepest laws ever discovered, written into space-time long before the first atom of Earth formed. In this video you will learn why the nearest star is effectively unreachable with any propulsion system we currently understand, why even traveling at 10% of light speed would require more energy than entire civilizations produce, why time dilation creates a trap that turns victory into isolation, and why popular ideas like warp drives demand forms of matter that may not even exist in our universe. You will also discover lesser-known scientific discussions that rarely make headlines, including the radiation barrier created by interstellar hydrogen at relativistic speeds and the brutal impact energy of microscopic particles when a spacecraft moves too fast. By the end, you will see that the real obstacle to interstellar travel is not funding, not politics, not even engineering. It is physics itself, and physics does not negotiate. This is not a story about pessimism, it is a story about limits. The same equations that allow GPS satellites to function also tell us that reaching another star may require bending rules we have never broken. The same relativity that explains how gravity curves space also ensures that no object with mass can ever truly reach light speed. These are not guesses, they are tested principles confirmed again and again in laboratories and particle accelerators, yet the dream refuses to die. Every few years, a new headline appears claiming that warp bubbles might be possible, or that exotic propulsion systems could break the barrier. Each time the excitement rises, each time the deeper calculations pull us back down. The truth is more dramatic than fiction, because it suggests that the universe may be fundamentally designed in a way that keeps civilizations isolated, not by intention, not by force, but by scale and energy, and time woven together into an invisible cage. Stay with me until the end, because the final piece of this puzzle is the most unsettling one. It is not just about distance, or fuel, or speed. It is about what happens to reality itself when you try to outrun it. By the time we finish, the stars above may look the same, but they will feel different. Smaller in brightness, larger in meaning, farther in possibility. Welcome to our channel, where we break down the biggest ideas in science with clarity and depth. If you are curious about the universe and want to understand what truly stands between humanity and the stars, subscribe now and join us as we uncover the physics that may make interstellar travel impossible. 4 light years sounds small when said quickly, but the number hides a scale that breaks the mind. The nearest star system to us is Proxima Centauri, part of the Alpha Centauri system, sitting about 4.24 light years away from Earth. 1 light year is the distance light travels in a single year, moving at 300,000 kilometers per second. In 1 second, light can circle Earth more than 7 times. In 1 year, it travels nearly 10 trillion kilometers. Multiply that by more than 4, and you begin to see the problem. The Moon is about 384,000 kilometers away. Mars, at its closest, is roughly 56 million kilometers from Earth. These distances feel huge to us. It took humans 3 days to reach the Moon during the Apollo missions. It takes months to reach Mars with robotic probes. Yet these distances are tiny compared to Proxima Centauri. If the distance to the Moon were the width of a small room, the distance to Mars would be like traveling across a continent. The distance to Proxima Centauri would stretch beyond the planet itself. Now consider speed. One of the fastest human-made objects ever built is Voyager 1. It is moving at about 17 kilometers per second relative to the Sun. That is incredibly fast by everyday standards. At that speed, Voyager 1 would take more than 70,000 years to reach Proxima Centauri. 70,000 years. When Voyager launched in 1977, humans had not yet built the internet as we know it. Recorded human civilization itself is only about 5,000 years old. Entire empires rise and fall in far less time than that. The universe is not built on human scale, it is built on cosmic scale. Our instincts evolved to measure forests and rivers, not light years and vacuum. And distance is only the first problem. In the early 20th century, a quiet patent clerk named Albert Einstein changed everything. His theory of special relativity reshaped how we understand space and time. At its core, the theory says something simple but brutal. The speed of light in a vacuum is constant and cannot be exceeded. It is not just fast, it is a fundamental limit woven into the fabric of reality. As an object with mass moves faster, its energy increases, its effective mass increases. Time for that object slows down relative to a stationary observer. To push an object closer and closer to the speed of light, you must pour more and more energy into it. But the closer you get, the more energy it demands. The requirement does not increase in a straight line. It curves upward sharply. At the speed of light, the energy required becomes infinite. Infinite energy is not difficult to obtain, it is impossible. This means that no object with mass can ever reach light speed. Not a spaceship, not a human, not even a single atom. Even reaching a fraction of light speed is a massive challenge. To travel at just 10% of light speed, a spacecraft would need to move at about 30,000 kilometers per second. That is nearly 2,000 times faster than Voyager 1. The universe has a built-in speed limit. It does not matter how advanced a civilization becomes. That wall remains. Now consider energy more closely. The kinetic energy of a moving object depends on its mass and the square of its velocity. Double the speed, and the energy required increases 4 times. Increase speed by 10 times, and energy increases 100 times. At relativistic speeds, the equation becomes even more demanding. Imagine a modest spacecraft with a mass of 1,000 tons, far smaller than many ocean ships on Earth. To accelerate that spacecraft to 10% of light speed would require on the order of 4.5 times 10 to the 20 joules of energy, even before accounting for inefficiencies or the fuel needed to slow down at the destination. For comparison, total global energy consumption in a year is roughly 6 times 10 to the 20 joules. That means pushing a single small spacecraft to just 10% of light speed could consume a large fraction of the energy humanity produces in an entire year, and that is only acceleration. You would need roughly the same amount again to slow down when you arrive. It is not just difficult, it is civilization breaking. You would need energy systems far beyond our current capabilities, and you would need to sustain them safely. And even if we had the energy, other problems wait ahead. At realistic speeds, the journey remains painfully long. Suppose we could build a spacecraft that travels at 1% of light speed, about 3,000 kilometers per second. That is still far beyond our current technology. At that speed, reaching Proxima Centauri would take more than 400 years. No single human crew could survive that journey in the normal sense. This leads to the concept of generational ships, massive vessels where multiple generations are born, live and die during the voyage. The people who arrive would not be the ones who left. Entire societies would need to function inside a closed metal world for centuries. Biological limits make this fragile. Humans require stable ecosystems, food production, psychological stability, and protection from radiation. Deep space is filled with cosmic rays, high-energy particles that can damage DNA and increase cancer risk. Earth's magnetic field and atmosphere shield us from most of this radiation. A spacecraft traveling through interstellar space would not have that natural protection. Shielding adds mass. More mass requires more energy. The problem compounds. Then there are micrometeoroids. Tiny grains of dust drift through space. At everyday speeds, they are harmless, but at a significant fraction of light speed, even a speck of dust becomes a high-energy projectile. The impact could release energy comparable to explosives. A spacecraft traveling fast enough to reach another star in a human lifetime would face constant bombardment. One failure in shielding could be catastrophic. Space does not forgive mistakes. As speed increases, relativity introduces another strange effect: time dilation. According to special relativity, time passes more slowly for objects moving at high speed relative to those at rest. If astronauts traveled at near light speed, time on their ship would slow down compared to time on Earth. For them, the journey might feel shorter. A trip that takes decades on Earth could feel like only a few years on board. At first, this sounds like a solution, but it comes with a cost. When they arrive, far more time will have passed on Earth. Families, cultures, nations, even languages could change beyond recognition. If they return to a future they do not belong to. Even at 50% of light speed, the effects are significant. The faster you go, the more disconnected you become from the timeline of everyone you left behind. The journey becomes not only spatial, but temporal exile. You leave your world not just in distance, but in time. Even if you arrive at another star, everything you knew may be gone. The psychological weight of that separation is rarely discussed. It means interstellar travel is not exploration in the traditional sense. It is departure without return. Science fiction offers an escape from these limits. In the universe of Star Trek, warp drive allows starships to travel faster than light by bending space itself. Characters like Spock calmly discuss warp factors as if they are routine engineering settings. Inspired by such ideas, physicist Miguel Alcubierre proposed a theoretical model in 1994 known as the Alcubierre warp drive. Instead of moving a ship through space faster than light, the concept suggests compressing space in front of the ship and expanding it behind, effectively creating a bubble that moves faster than light relative to distant observers. Inside the bubble, the ship would remain locally stationary. On paper, the equations of general relativity allow such a solution, but the catch is severe. The model requires exotic matter with negative energy density, something not known to exist in usable quantities. Negative energy appears in small effects in quantum physics, such as the Casimir effect, but only in tiny amounts. The original calculations suggested that the amount of negative energy required could be comparable to the mass energy of entire planets or even stars. Later revisions reduced the estimate, but it remains enormous and speculative. No known mechanism can create or control such matter on the needed scale. Mathematics allows it, reality does not. All these barriers stack together. Distance stretches beyond intuition. The speed of light stands as an absolute ceiling. Energy demands grow beyond planetary capacity. Human biology struggles against radiation, isolation, and time. Relativity twists the timeline itself. Each obstacle alone is intimidating. Together they form a wall that appears almost unbreakable. The universe may allow us to look at the stars, but not to reach them. After all these barriers, the perspective begins to change. Maybe the future of interstellar exploration does not belong to fragile biological bodies. Maybe it belongs to machines. Robotic probes do not need air. They do not fear radiation. They do not suffer from loneliness. A tiny probe, powered by advanced lasers or nuclear systems, could one day travel faster and survive longer than any human crew. Projects already being studied suggest sending gram-scale spacecraft toward Alpha Centauri using powerful light sails. The journey would still take decades, but machines can wait. Machines do not age the way we do. Or maybe the frontier is not physical at all. Some scientists and futurists suggest that consciousness itself could one day be digitized. If minds could exist in non-biological form, the limits of food, oxygen, and many biological weaknesses would fade. A digital traveler could endure centuries. It could move through space in ways we cannot. This idea sounds distant and controversial, but so did landing on the moon just a century ago. The direction of progress often surprises us, and then there is the possibility we rarely talk about. Maybe we are meant to stay. Maybe the lesson written into physics is not about escape, but about responsibility. Earth is not just our starting point. It may be our only true home. The distances between stars may not be an invitation. They may be a warning about scale, fragility, and limits. If the universe has made travel between stars almost impossible, then survival here becomes the greatest mission of all. Cosmic isolation does not mean cosmic insignificance. It means rarity. It means that life, consciousness, and civilization might be precious beyond measure. Instead of dreaming only about distant suns, perhaps the real frontier is solving energy, climate, biology, and sustainability here on this small world. Perhaps mastering our own planet is harder and more important than crossing to another. The laws of physics are not obstacles placed in our path out of cruelty. They are boundaries that define the game. Understanding them does not kill wonder, it deepens it. The stars remain beautiful, they remain mysterious, but now they also represent scale, humility, and perspective. So here is the final thought. If interstellar travel pushes against the very structure of space and time, then maybe the greatest achievement of humanity will not be escaping Earth. Maybe it will be learning how to thrive on it for thousands, even millions of years. What if the greatest discovery isn't how to leave, but how to survive where we are? If this video changed the way you see the universe, make sure to like it, share it with someone who loves space and big ideas, and subscribe to the channel for more deep explorations into science, reality, and the limits of what is possible. The journey of understanding has only just begun.